In this video, we're going to go through how to find the derivative of any function with a power using the shortcut rule. All of these examples have been completed. So what I'm going to do is I'm going to talk you through each one. For this particular example, f of x equals to 8x to the power of 3. If we take the power of 3 and multiply it with the 8 at the front, take the power, multiply it at the front, then subtract the power by 1. So we're taking the power, multiplying at the front. 3 times 8 is 24. Then you subtract the power of x to the power of 3 by 1. It becomes x squared. That's it. Take the power, multiply it at the front. 4 times negative 3 is negative 12. Subtract the power by 1. So x to the power of 4 becomes x to the power of 3. For part C here, take the power, multiply it at the front. 3 times 3 is 9. Subtract the power by 1. X to the power of 3 becomes x to the power of 2. And since there are 4 terms in this question, 1, 2, 3, 4, you will do this on 4 separate equations. So 4x squared, negative 4x squared becomes, oops, notice the mistake there, becomes negative 8x, subtract the power by 1 as well. 3x becomes 3. Let me break down this one here. I'll zoom in a bit. So when you differentiate, I'm going to use the operator notation here by differentiating 3x. Essentially what's unseen here is x to the power of 1. When we go to differentiate this, we are going 3 times this one, take the power, multiply it at the front. Then you've got x to the power of 1, but you subtract the power by 1. Okay, so take the power, multiply it at the front, then subtract the power by 1. We're going to end up with 3x, subtract the power by 1. 3x to the power of 0. X to the power of 0 is 1. Therefore, you end up with 3. So if it's x to the power of 1, it becomes x to the power of 0. The variable of x disappears. However, you keep the coefficient at the front. And this negative 10 here, since there is no x attached, the power of x disappears. I'll show you why. Because the algebra here still checks out. I'll demonstrate. If we take, I'll do this in green here. We're going to apply the operator notation to negative 10. Essentially, negative 10 is multiplied with x to the power of 0. It's like as if it's there, but it's not there because x to the power of 0 is the same as multiplying by 1. So if we apply the same rules here, take the power, multiply it by the coefficient, and then you can subtract the power by 1 if you wish to. But because 0 times anything is 0, your final answer is 0 anyway. So it checks out that down at the bottom here, we end up with a plus 0. I'll keep these two calculations here handy as a demonstration for whenever we come across that situation. In this example here, take the power, multiply it at the front, end up with -8, subtract the power by 1. 5 times 3, take the power, multiply it at the front, subtract the power by 1. -12x, if you take the power, multiply it at the front, subtract it by 1, you'll end up with just the coefficient at the front, just -12. The x disappears completely. Notice at the front here for each of these examples, f of x, after you start applying the power rule, it becomes f dash x. In this next example here, we are using Leibniz notation because we have a y at the front. So if we want to show our derivative, it is dy dx. The same rule applies. Take the power, multiply it at the front. Oops, that should be a 6. Then you subtract the power by 1. Take the power, multiply it at the front, subtract the power by 1. This here is a constant similar to that top one, so it becomes +0. In part B, notice here how we do have 2 brackets. What we can do is expand the brackets in this particular case. But notice when we expand the bracket, we have not started our process of differentiation yet. Therefore, the front, our subject is still equal to y. Once you have expanded the expression or the equation here, then you can differentiate. Take the power, multiply it by the front, then subtract the power by 1. Likewise with the 8x. -8x turns into -8. Same here. Make sure you simplify the expression first by splitting up the denominator and divide both terms in the numerator, both terms here separately, so that you end up with a simplified expression. Once you have a simplified expression, then you can differentiate. Leibniz notation on these 3 questions here. For part D, we have the operator notation. Nothing to equal at the front. Because this is an expression, our answer is an expression. Follows on. These questions down at the bottom here, for your turn. These are also the derivatives. We are using Leibniz notation here, so dx dt. Notice that we are differentiating in terms of t. Leibniz notation again. We've got z and x, so it becomes dz dx. Third one here, make sure you expand the brackets first and still equal to y. So we're expanding the brackets, then you differentiate. dx, Leibniz notation, dd dx. Operator notation, just a simple equals. And function notation, so you have the dash when you differentiate, v dash of t. And this example here is similar to our previous example at the top, where you must split the terms by dividing by the denominator. So have a look through, pause, rewind, rewatch if you'd like to revise.